Hello, everyone. My name is Dan Jonas Roach, and I am the news editor here at the Architects newspaper. I'd like to welcome you all to the Building Perfect Wall with Insulated Metal Panels live webinar, a CE Strong webinar series powered by the Architects newspaper. This webinar is sponsored by MCA. This program is registered with the AIA CES for continuing professional education. Questions related to specific materials, methods, and services will be addressed at the conclusion of this presentation. This webinar is recorded and can be easily replayed when re-registered on the same webinar registration page. Please allow 7 business days to process certificate of participation and AIA credit reporting for this presentation. We encourage you to ask questions using the Zoom Q&A button found at the bottom of your Zoom window. Now, I'd like to introduce you to today's presenter, Tim Leach. Tim has over 20 years of experience in the metal roof and wall panel market. He has held various roles in estimating, sales, project management, and business development, interacting with architects, GCs, and installers. In his current role, Tim spends much of his time discussing concepts related to the design and performance of insulated metal panels. Remember to please leave your questions for Tim in the Q&A window. Without further ado, Tim Leach.
Thank you, Dan. Let me get this opened and we'll get going here. So today, of course, we're talking about building the perfect wall with insulated metal panels. We're going to let me just kind of talk about the learning objectives here. That we're understanding the natural forces of hygrothermal loads, heat and moisture, acting on building envelopes, how to design walls to deal with that. We're going to learn some design considerations for rainwater, for air movement, for pressure differentials, and for vapor control. And then, of course, we're going to also look at how an insulated panel, obviously, how it performs those functions as a single component and has can be a perfect universal wall. And then we'll talk a little bit about integrating things like windows into that system. So first, we want to talk about environmental loads, what those environmental loads are. And we were talking, of course, about water, heat, air, and air vapor. Water, of course, is the most important thing to control. If you're not controlling water inundation through your walls, you're certainly not going to be able to control anything else. So it goes down from water to air vapor, and then finally thermal control, that heat gain and loss. So we'll talk a little bit about some basic physics first, just to kind of set the table. First of all, we talk about those environmental loads, and you have a chart here that says, heat flows from warm to cold, moisture flows from warm to cold, moisture flows from more to less, water vapor moves from moist to dry. Basically, what we have here on this list when we're talking about these things is more energy moves towards less energy. So, air pressure has more energy than low pressure. Nature abhors a vacuum, so it wants to try to equalize that. And so your wall design has to take that into consideration. And we also talk about heat. We have here this nice little illustration. You've got your radiation, in this case, a campfire. It can be the sun, of course, and that is your heat source. It's radiating outwards, and it's heating up the pan in this example. Inside that pan is water that's heating up, and as it heats up, it rises in the pan, and it circulates, and so you get convection. But then we got the pot handle, and that's something really we kind of focus on more than any of this when we're talking about wall design, because that's that thermal bridging, that conduction. So when we have a situation where you have metal or some other material that's touching the outside face that can get warm and it can conduct that heat into the building, then we have what we call a thermal bridge, and we want to find ways to reduce that as much as possible in our wall design. Then we have, of course, moisture. Vapor diffusion is a big issue because water vapor has that energy, it has that drive. It's going to find its way through small pores into a system, and you get the vapor diffusion. But you also can have air transported moisture where moisture that's built into something, humidity. If you add energy like wind, like air, pushing into the surfaces, it will find its way through and move into your wall and into your building. So you can see, of course, these are some simple sorts of concepts. Of course, also as far as simple here, liquid moisture. And when we talk about metal panels, we think about the rain screen principle of a metal panel. For that outside rain screen, we want to have a panel that accounts for how water moves. It moves due to gravity, rain falling down. It moves with kinetic energy. If you add wind and it blows into that wall, it moves upwards or sideways due to capillary action. When you have two surfaces close together and the water is in between, it can work its way upwards. Then there's the surface tension, that outside surface of the material where the water can stick to it, and you want it to drip away. And then, of course, finally, you have that pressure differential. Certainly, if you have wind pushing into a building, you can have a pressure differential with high pressure outside and low pressure inside, but it doesn't need to be wind, because you can have high pressure, relatively speaking, on the outside of a building, and high pressure wants to move to low pressure. It wants to equalize. So we have to consider that whenever we're looking at our wall design. Then we also want to be sure that we're looking for fail-safe. So when we talk about walls and we talk about how they're structured, we also have to be concerned with how walls fail. And here's a couple of examples of wall failures. They're not, of course, the only failures, but you got salt deposits on this one surface here on the left. You see this masonry wall with that white chalky surface. That's salt deposits. Couple of ways that can happen. Of course, obviously, there could be salts that are deposited on street level and during the winter time, and that mixes with water and the water splashes up on the building. But you can also have effluents where there's other types of chemicals that are doing this, that are working into, in this case, this porous surface of the masonry. So anytime you have that sort of surface, you have to be aware of how, of course, that water is going to migrate, but it may leave behind other materials like these salt deposits. Then to the right, you have ice formation. In this case, we have a metal roof and we have a brick wall. The metal roof is probably, in this case, much colder than that brick wall, because the brick wall during the daytime absorbs some sun, heats up. The roof does not during the the later hours. You get ice built up. Of course, the ice will melt, but when that ice forms between that brick and that metal surface, obviously ice can expand, it can crack, it can open up wall areas, and you can have some water inundation. So again, there's a lot of ways that we could look at, you have to design your wall to against failure. Now, there's also concealed failure. In this case, water intrusion in through systems. Like we said, water vapor wants to move into the walls. If you have significant water intrusion, like you see here on the left, you can see these are galvanized studs that have been exposed to water for a long time. And of course, there's probably some minerals in that water that are acting on that galvanizing. And you could see that even though it's galvanized, there's a lot of rust here. But remember, this is probably in a concealed area where this happened over time and no one is able to see it. That's where the problem exists. And same thing for this mold and mildew. It's concealed, and so it has to get bad before you even notice it. So those are some examples of things we don't want, of course. So let's talk about those environmental control layers and what we need to do, what we need to think about whenever we're designing walls. First, of course, we have to control water, the bulk water, rain, groundwater, that sort of thing. Then we also need to deal with thermal control, heat loss or gain. We need to deal with air control, air tightness. We always talk about in modern building design, tight buildings, and that's what we mean is that tightness. And vapor control. So air and vapor certainly can act the same sort of way to wall structures, but we're breaking each one of these out so we can look at them separately and do some comparing and contrasting. But we're going to look at each one of these one at a time and talk about how to design your wall. And we're going to look at, in this case, other types of structures. So water control. First, we have mass walls here. And in this case, tilt wall precast sort of structure, concrete walls. The issue here is once the moisture gets into that wall, you've lost the battle as far as moisture is concerned. It's slowly going to release moisture through evaporation, and some of that moisture is going to travel into the building. It lacks redundancy because the control layer is going to be to the outside surface of that wall. So that's one thing about mass walls, that they're good for certain purposes, but they're not great for water control. You have an example of barrier walls. You see this a lot in like pre-engineered metal buildings where you have a single skin metal panel that's pressed over some insulation. Again, you have a single line of defense, that metal panel, and there are seams of those panels that provide capillary action of water to allow that water inside the cavity. And you have, in this case, an insulation type that can hold moisture. And so if that insulation holds moisture, it's going to lose its effectiveness, its R rating. So it lacks redundancy. We don't want that. Now we're going to look at something a little bit more mainstream as far as controlling the water and a lot of other things. The rain screen principle of panels. You've got your outside rain screen, that's your water control, but behind it you have your weather barrier system that consists of insulation, vapor barrier, sheathing, and other materials. So this is more of a direct comparison to insulated panels. So insulated panels have all those layers. We have the outside face is your rain screen. The inside face is your air barrier and your vapor barrier. And then of course the foam in between is your thermal barrier. An insulated panel, and we'll talk about this a few more times, is a barrier system. With that sealant at that joint, with the sealant around the panel perimeter, with that metal face, it is a barrier system. There's no way for air or vapor to move through that system. And you can see in this picture, you have technology like dual joint system. That inside joint is your sealant joint. The outside joint is adding strength. It's also adding a baffle for any rainwater that splashes into that panel joint. And you've got the single component, single insulated panel that's doing all the work in one unit. Now, we also have, in this case, what we call a pressure equalized joint. We were talking about the pressure differential. Whenever you have that high pressure outside and low pressure inside, and a good rain screen panel deals with pressure equalization, which just basically means those pressure differentials can be handled with the panel without it creating additional suction to pull moisture with it. In this case, it's kind of like a straw. If you think about a straw, you put a straw in a Coke and you suck on the straw, what you're doing is you're creating negative pressure inside the straw to pull the moisture, the fluid up that straw. So the negative pressure inside the straw is relative to the pressure outside the straw. But if you accidentally bend that straw and you create a hole in that straw, now when you suck on that straw, the pressure is equalizing from the outside to the inside without necessarily pulling much of any moisture or fluid up that straw. That's pressure equalization. So a rain screen panel should look at that pressure equalized joint. Okay, so when we're talking about water control, we're also talking about, you could see in this example, the vertical joints of a horizontal insulated panel. You can see the sealants that are involved there. That's a big part of how an insulated panel works. You've got hydrostatic pressure here, pressure exerted by a liquid at rest due to gravity. And in this example, we have the panel joints where the water by gravity will flow outwards. And even in that middle joint there, you've got your parallel sealants and basically a channel down the middle of that joint to move the water to the outside. It doesn't have a path to the inside. That's what you want. Okay, let's talk about thermal control. Of course, again, we're talking about this rain screen principle. In the rain screen principle, we usually have some sort of exterior rigid insulation. We may also have some cavity fill insulation in that same system, depending on building codes and building design. So exterior rigid insulation is outside the structure of the building, so you get a much more consistent, or in some cases, what you'd call continuous insulation. And then your cavity-based insulation, if you use cavity-based insulation by itself, what you're doing is you're having every one of those studs or other structural members are causing short circuits to your insulation. So cavity-based insulation by itself is not sufficient for good thermal control. You really want that exterior rigid insulation. It's best to have your insulation, most if not all of your insulation, outside the structure so it can be more consistent. So let's talk about insulated panels. Where do they exist? Well, they attach to the structure, so they're outside that structure. They're more consistent. You have that thick foam that's usually going to be a polyisocyanurate type of foam that has a really good insulation value, around an R8 or more per inch. And it's, again, consistent because it's outside the structure. So that's your thermal control. Air control. Now we're getting into the harder things to control, quite frankly. Air-water barriers. We have, of course, an insulated panel is a barrier system. And I'll keep on saying that that's a barrier system. When it's installed with the sealants, there's no room for air to move through that system. The foam is closed-celled, so there's no way it's going to absorb air. The metal facing is, of course, solid. It's not going to allow air through there, and there's sealants around it. We're protecting against air-water penetration. Now we look at a couple of other examples here. When those mass walls, we need some sort of fluid applied system to the outside face. One of the issues there is getting that consistent. You can see in this case, someone is spraying. If you imagine a big mass wall that's, say, 40 feet tall and 300 feet long, and having someone spray that consistently, you can realize how human error can really cause you some issues there, either over applying in certain places or under applying in other places. So that's one issue with mass walls. Then we have building wraps that can control air movement somewhat, but we'll get back to that here in a moment when we talk about vapor control. So we see that air barriers often serve double duty as vapor retarders. So let's go ahead and jump and talk about them also. Whoop, wait a second, I forgot that we're also going to talk about air control just for a moment. We were talking about the pressure differentials. Whenever you have wind pressurization, you have one side of a building that's going to have high pressure and one side of the building is going to have negative pressure relative to what's inside the building. And whenever you have those pressure differentials, one way or the other, we can assume that it's high pressure and we can build a wall for that. But you also have negative pressures, which is suction outside of the building. So your wall has to deal with both directions, really. And then you can have mechanical pressurization where either there's pressure outside the building relative to what's inside, or if your HVAC is kicked on and you're pushing air through the building, you could pressurize the inside of the building relative to the outside. And of course, then you have to worry about leaking of that pressure. Okay, so now let's get back to the vapor control layer. We were talking about air control, and it's very similar to vapor control. There are two types of vapor control layers. Barriers, which an insulated panel, again, is one. Your inside face of that panel sealed against the structure of the building, with the panel joints being sealed, it is a barrier system. So the vapor does not have a direction to move through that wall. You can say that, and we'll talk about this later on, that any moisture that's outside that wall stays outside. Any moisture that's inside the wall stays inside. It has to be dealt with there. We have an example of another type of barrier system, this polyethylene sheathing you can see. One thing about this, I love to point this picture out. Of course, you can see Obviously, it's stapled along a lot of joints, and as long as that's handled correctly, everything's fine. I can also see some electrical outlets that have special taping around them so that, of course, it's a barrier system. You're trying to be sure that it's all nice and complete. But in this case, I love this picture. This polyethylene sheathing is clear. So how do you know that there's a rip somewhere or not? And then, of course, you have to deal with, you've got your electrical people who are going to come into this building, your plumbing people, your drywall people, and how do you know that someone didn't accidentally rip a hole in this section somewhere? So that, a hole in that system ruins it because it is a barrier. It needs to be complete. An insulated panel being a solid material, you're not going to just rip it open. So it's a more effective barrier because it's visible. You can see that it's a barrier system. Now, other than barriers, we have retarders. So what we're talking about here, like building wraps, liquid applied systems, vinyl paper on batt insulation, latex paint on gypsum, all these types of systems are limiting the amount of water vapor moving in and out of a building, but they're not excluding it. They're not a barrier. So they're what we call breathable. And I can look at this building wrap as an example of that. And there's an apartment complex near where I live that was being erected last year, and they were applying the building wrap like you can see in this picture. But there's, if you've ever seen that, there's really a couple of steps. First, you lay it out on the wall, you tack it in place, and then you're going to cut the holes for the openings, and then you're going to come back and you're going to secure it, and you're going to tape those openings and do all those stuff to make it permanent. But on this apartment complex, they had just done that first step. They had laid it out and tacked it in place. And then we had a little Hurricane Beryl blew through. And it was a category 1, a lot of high winds, a lot of rain, of course, as hurricanes will do. And this system came loose in a few places, but it didn't tear because it's a really robust fabric. A couple of days after that storm, the same crew is back on this job, tacking that same material back in place. The problem is they did not allow enough time for the OSB that's behind it to dry out. So it is breathable, but it's not that breathable. And so the chances are they're going to cause some problems down the road. But that really highlights a point for some of this other material that I want to contrast an insulated panel. And that is an insulated panel, because the foam is non-hygroscopic. The metal surface doesn't absorb moisture. It is not as weather dependent in installation as some of this other material. An insulated panel, a few hours after a rain, you can continue installing because it's nothing, the panel is not going to be affected by the rain. These building wraps, yes, you're really going to have to stop and maybe even start over if, like in that situation, the whole undersurface gets saturated. The liquid applied, of course, obviously you're going to need a good weather day to be able to do that on the outside of a building. You certainly couldn't do that on a rainy day. So a lot of this other material can be delayed on a job site because you have to worry about weather, where insulated panels are one of those types of materials that's really not as weather limited. That's a good thing to point out. Okay, so proper vapor control, and this is important, it depends on the climate zone, the insulation system, building use, and interior conditions. So the climate zone, of course, is it a hot environment? Is it a cold environment? Is it a wet environment? Is it a dry environment? The insulation system, where that insulation is it rigid? Is it in the cavity? Is it both? The building use, is it an office? Is it a pharmaceutical facility? There's a lot of different types of building use that could either require a really dry interior or have elevated moisture. And so that vapor control needs to be designed based on that information. And then, of course, like I said, the interior conditions. So whenever we're looking at vapor control, this is one of the ones, like I said, is really one of the most tricky ones to deal with. Let's talk about then what would constitute a perfect universal wall. So we'll start out with the basics, and that is the exterior cladding resists the majority of the rainwater. So we're talking about a rain screen principle here. Exterior rigid insulation would be that next layer. The air vapor water membrane is inboard of that thermal control layer, and all of the above are exterior of the building structure. Now, this describes, again, a rain screen principle system, and probably 75% of rain screen panels, rain screen walls are built this way, with the rigid insulation being the outside layer, then the air and water membrane being inboard of that. However, we have to deal with climate zones, different climate zones and different work environments. So now some of those walls are not perfect. They're not built correctly. Perfect universal wall design is a simple, elegant solution designing code compliant wall assemblies. We need to have something that I don't have to sit here and worry about cold climates versus hot climates. So here's what I mean. Cold climates, that air vapor secondary water control layer should stay warm. That means it needs to be inside the insulation. Okay, we kind of have that in that previous example. Hot climates, the air vapor secondary water control layer should be on the exterior. It allows evaporation and drainage. Whoops, now we got a problem if we did it the other direction. Now, okay, let's say I got a hot climate. I'm going to put the vapor layer on the outside of the insulation. Okay, well, what time of year is it? In some of these climate zones, you have, hot seasons and cold seasons, wet seasons and dry seasons. And now that vapor layer really starts to get to be a complicated decision, where a single component like an insulated panel solves that because it's a barrier system. We're not worried about where the control layers are. We know where they are. The only difference in an insulated panel for a hot system versus a cold system is the thickness for the insulation value. But it's an air barrier, it's built-in vapor barrier, it's robust outboard insulation, and then you get some great aesthetics with it. So your traditional assembly, you take all those units, that rain screen, the hat sections, the thermal layer, the vapor barrier, and the sheathing, and you combine all that into an insulated panel. So you have one unit, you have a single source responsibility because there's only going to be one material to install, one crew, one pass around that building. It's a faster, simpler, cleaner way to do things than using this multi-component system. And because it is a barrier system, because it is that metal panel, it can actually be something that provides a weather tightness warranty to go along with it. Okay, so if we're going to build with those systems, we need to know a few little things here. So I said that it's a barrier system, and that means there's a dual vapor profile. What does that mean? That means that the vapor, the moisture that's outside the building is going to stay outside, and any moisture that's inside the building has to be dealt with inside the building. It doesn't breathe. It doesn't move through the system. The drying occurs to the exterior from the outside face. The drying occurs to the interior from the inside face. Panels are non-hygroscopic. They're not going to absorb moisture themselves. So the moisture is going to be dealt with outside the faces. Okay, quick thing, whenever we're dealing with insulated panels in this situation, we should not add a vapor barrier to this assembly because it is a vapor barrier. Remember that. Okay, IMPs provide all four control layers in a single component. That's the thing. It simplifies that wall design. Okay, do I need a hygrothermal analysis when using a perfect wall design, using an insulated panel? So what is a hygrothermal analysis? It's an analysis of how the moisture is dealt with inside the building. So the design is universal and works in all climate zones. We're not worried about should the vapor layer be outside the insulation or inside the insulation, that sort of thing, because the insulated panel is one component. We're not worried about the components being stacked in different directions. So we don't have to do a hygrothermal analysis if we're using an insulated panel. Now, can I add supplemental insulation to that perfect wall, to that insulated panel? So there are situations where people want to add insulation in that cavity behind it, and there's frankly, some misunderstanding of energy codes that sometimes drive that. We could talk about that a whole different time. But can you add insulation if you need it? Well, yes, you can. But now, because you could have a situation with a dew point inside that insulation, now I really do want to do a hygrothermal analysis to be sure that I'm not going to shift that dew point into the insulation, or how to deal with it to be sure that that doesn't happen. Don't add a vapor barrier to this system, especially to this system. Okay, so can I use a supplemental air water vapor barrier to the interior of a panel system? So the last two slides you saw what? Don't add vapor barriers to the system. But the question is, can you do it? And the answer, of course, is yes. But here's the key. If you're going to use a vapor barrier inside, and there are some reasons for doing this that we could talk about for quite a bit of time, but if you're going to do it, it needs to be permeable or semi-permeable. In other words, it needs to be breathable towards the inside, because that inside face of that panel is a barrier. And if you put a barrier over a barrier, you're going to trap any moisture that's in between. So if you're going to do a air water vapor barrier to the inside face of an insulated panel, be sure that it's breathable. Okay, so other considerations to remember is we're talking about walls, but you have a whole building here. You have roofs also that you're going to deal with, and whatever situation you have in your roof, in this case a roof membrane, that membrane needs to continue to the wall surface. Those two need to connect in order to work properly. You can't have a gap between the two of them. That should go without saying, but it needs to be said. That those whatever surfaces you have for a roof versus your insulated panel, those need to mate together. So wall-to-base transitions. When we talk about an insulated panel, especially a horizontal panel, here's a picture of what that base looks like. You've got your panel joint, and you can see there's usually like a starter extrusion that the panel would sit on. And if you left that alone, you would have an air gap. So you would have an issue with some poor insulation quality right at the bottom of your wall, which would be a bad situation. Here's one way that can be addressed, of course, is just to add some supplemental thermal insulation. But there's another suggestion, of course, whenever you're designing a wall panel using insulated panels, bypass that panel below the finished floor, and then you don't have quite that problem. And you can see in this example, it shows that the panel kind of sticks out from the foundation and has some supplemental insulation there. But the point there in the picture, though, is that if you start the panel below that finished floor, it makes a much more airtight situation for the insulated panel. Okay, talk about continuity. Here's the pictures of kind of a typical picture of an insulated panel at a window opening. And we can see, of course, on the left picture, you see that air gap we were talking about. Probably shouldn't insulation in that air gap. But then below it, you have your flashing that's providing a flat surface for that window. And you see in the middle picture, that's a jamb. And again, you got that flat surface. And on your right, you see a seal. Now, what you're probably seeing, if you know what you're looking at, is you're seeing thermal bridges. You're seeing that metal going from the outside face to the inside face. And here you've got this perfect thermal barrier of an insulated panel, but at these window conditions, now I've created thermal bridges. So this is one issue that you have with an insulated panel. This, typically you got to have a window, you got to have doors, you got to have other materials. So how do you deal with it? Well, for windows, and we're talking specifically windows, one way that you can do that is to integrate them. And here's an example of how that can be done. Basically, what you have is a set of extrusions that follow the joinery pattern of the panel itself, and so the window frames can stack in the panel joint. And you can see on the left side, it's just the extrusion is joining over the window, over the panel, excuse me. And then you've got your glass there. So the glass would be provided by others. They'd just be the extrusion that would be provided by the insulated panel manufacturer. What this does, of course, it gives you a much more consistent thermal picture there at that window. You've got some thermal breaks there. And you got a nice clean look around your windows. Here's a little bit clearer, closer picture. You can see with the arrows, there's that thermal break. So you have two extrusions that are held in dimension with that thermal break in between. And then you have thermal insulation in certain places where there may be an air pocket. And then you have your sealant. So this panel, this extrusion, excuse me, is going to install just like another panel, but it's going to give you a nice integrated clean window and give you some a much better thermal image than that system that would have flashing going to the inside of the building. So that's something that can be done, and it's not just windows that you can do this with, but you know, it just depends on who's providing the materials, what sort of details they have. So one more quick point to talk about when we're talking about insulated panels, when we're talking about that range screen principle, we've got all those parts that we're replacing. But what if I want some profile panels like in this picture, this beautiful picture here? So to the right, you can see those flat panels. Those are aluminum panels. And to the left, you can see the profile. Those are metal panels. And in another part of this job, you will see that there's some masonry. So where's the insulated panel in this? Well, it's behind that system. So that layer of air, water, and vapor barrier doesn't have to just be your outside face. It can be a concealed system. So instead of having, again, a vapor layer, a vapor barrier, a thermal layer, some other sheathing, you can use an insulated panel to do all that. And what you have in this picture, I will point out, you'll notice that the windows are closed. You'll notice that the doors are sealed up. That's because now that this panel is installed, you have a sealed in building. So they can work inside the building as though it's dried in while they're coordinating all this other work. So instead of the multiple passes that you would have with the different systems and the multiple trades you'd have with the different systems and trying to coordinate that and being sure, okay, does the vapor barrier need to be on the outside or the inside? You can just put an insulated panel in place and have that perfect universal system. And so then you can have it looking like, oops, right at the end. Beg your pardon. Let me get back to, there we go. Sorry, clicked the wrong button. So here's the example of some of that concealed panel system. There's the, you know, you've got range screen panel on one side, you got some terracotta type material in the middle, and you got brick on the other side. Point being, there's multiple ways to use this insulated panel, and there's different types of clips and hat sections and other attachment points that can be used outside that that panel system to attach other materials. And then you have your concealed panel behind it. So insulated panels. Insulated panels provide a 5-in-1 design for your air, vapor, and water and thermal barriers in a single component. That's the big thing about an insulated panel. What makes an insulated panel a perfect universal system is it's just one design. You don't have to worry about all these other components and which one should be located where. It functions as a perfect universal wall because of that. It's got the same control layer functions as multi-component walls. So instead of having to deal with all those different components, you got a single component. Simplifies that wall system. Simplification, that's the big key for insulated panels. And that can, of course, provide significant labor and time savings versus those multi-component assemblies, like I pointed out a couple of times. Single source responsibility, so it makes it a lot easier for that design, and it can provide a weather tightness because of that. And it provides an ultimate envelope protection, whether used as a standalone cladding or a barrier wall system. And one of the best parts are, of course, it meets or exceeds all current code requirements for insulation and air barriers. You can have a really good performing system better than a lot of other systems that you have out there. But that's why an insulated panel is worth consideration. And this concludes my presentation.
Thanks, Tim. I'm going to start reading some questions.
Okay.
First question, can IMP be considered as a continuous installation or not? If not, do we need to use U factor per table C402.1.4?
Yeah, that's a very, very specific and good question. I appreciate that. Of course, an insulated panel, the continuous insulation, the definition excludes wall panels. And of course, also an insulated panel, you have that joinery. So it's not considered continuous insulation. But yes, as was pointed out in that question, you can look at the U value because it is consistent. It's outside the structure and it provides a really good U value. So yes, whenever you're looking at the building code, there are different ways to approach it, and the U value approach is the way we always recommend when we're talking about the insulated panel.
Great. Can you use IMP on the back side of the parapet wall?
Yes, you can. Certainly, again, when we're talking about that continuity earlier from a roof to a wall, if you have a parapet condition, you can certainly use the insulated panel on both sides of that parapet, the outside face and the inside face. Again, at the very top of it, you have to be concerned with continuity. There needs to be some sort of insulation, something that's connecting those two surfaces.
Do all IMP manufacturers provide integrated windows?
Well, to say all, I would say that there's, I would say the major providers provide something that integrates. And there's different designs, of course, depending on the panel, depending on the manufacturer. But to say do all insulated paint, I don't know that. I just know that the ones I'm aware of have some sort of system.
Cool. What would the average square foot cost be for a residential project?
You know, one of the best answers I've heard on cost is, of course, with insulated panels, we've got thickness, we've got gauges, we've got colors, we've got quantities. There's a lot, and we got profiles. We got different types of panels. There's a lot of different variables there, and it could be, you know, it could be like $8 to $10 a square foot for a really low price panel, up to, the sky's the limit for more architectural specialized types of panels. So it's really difficult to put a real price range without knowing a lot of information. But that's certainly something. You reach out to your to an insulated panel manufacturer. They can certainly work through that with you and narrow it down, and then be able to provide you some price range.
Great. Can IMP be part of a fire rated assembly or does it depend on foam type?
Okay, so IMPs have good fire testing considerations. The polyisocyanurate. However, a polyisocyanurate insulated foam does not provide your 1, 2, or 3 hour fire rating. You can use an insulated panel with layers of gypsum to create that fire rating. There are also other types of insulated panels that use mineral wool cores that can provide those rated systems. So there are options for fire rating, but going back to just your regular insulated panels, they do have great testing for your fire classifications.
What are typical adjustments made to the system to accommodate seismic movement for very tall panels?
Very tall panels, seismic movement. Okay, so insulated panels, of course, being metal, they do have some room for flex, but they are that insulated core does provide a lot of stiffness to the panel. So when you're talking about something like that, you're probably going to have, depending on what the height is and what the conditions are, you're probably going to have some expansion joints of some sort. Again, that would be something that would be there are different designs available depending on what's needed.
What are the anti-corrosion measures used in the metal panel facing panels?
Okay, yes, that good question. So, of course, insulated panels typically would use steel, and it's either going to be a galvanized like a G90 or a Galvalume. If you're dealing with corrosion, you really need to have the Galvalume system because that gives you a corrosion warranty, where G90 does not. G90 is still galvanized, it still can provide some corrosion resistance. Beyond that, of course, obviously, is the paint system that's going to be applied over it. And there's different levels of paint systems. You know, your typical paint is going to be roughly a 1 mil system with a primer and a color coat. But there are other builds, as they call them, you know, multiple layers of primer and clear coats and other systems depending on the environment. So those two acting in concert can provide corrosion resistance.
Um, this is a question from Angel. How can Angel get a list of providers in Florida?
Well, I mean, I think the easiest way would be, you know, hit the internet and look for insulated metal panels. There's plenty of sites to pull up and the sites usually have a um, some sort of button or whatever that tells you how to locate a rep.
Cool. Does the polyiso between the steel sheets absorb water? If so, what are the steps to avoid this issue?
Okay, so polyiso is a closed cell system. It's non-hygroscopic, which means it will not absorb water. And that's one of the great things about polyiso. That's what provides such a good thermal value in the system. So no, it does not. It does not absorb water.
Soffit conditions can cause water to move horizontally. Do you have examples of dealing with that?
They can move horizontal. And we were talking earlier about the rain screen principle. So even with a with an insulated panel, you have to have that idea of the rain screen principle. Um, and surface tension, water wanting to drip along that surface. Of course, there's obviously in a soffit situation, maybe there's some drip edges that would be included, but the panels themselves at their joints, usually, if you look closely at how a panel joint is shaped, there's a lot of thought that goes into that joint, and one of the thoughts is how to break that surface tension and cause the water to drip off the face of the panel.
What do the thermal expansion joint considerations look like in an IMP system?
Thermal expansion. Well, so uh, certainly, first the insulated panel itself, the way an insulated panel deals with thermal expansion is bowing. It'll bow out a little bit. The panels are designed to deal with that in and of themselves. But of course, if you're talking about thermal expansion on a large scale, you're probably talking about some sort of expansion joint somewhere along the building. And again, it would be, just depends on who's designing it, what that would look like.
If the wall assembly is an IMP, i.e. stud wall and gypsum, should the empty cavity between the IMP and the gypsum be ventilated? Will there be issues with the still air in this cavity?
Okay, so that's an interesting question. Of course, one of the things we talk about is that hygroscopic. The word about moisture accumulation. If you have dead airspace, like if you have insulation where it can hold that moisture and accumulate that moisture, then I'd be more concerned with that than I would just an airspace with gypsum on the inside and the insulated panel on the outside. You should have very little concern of moisture buildup in that situation because the insulated panel is providing a nice, if the inside is warm, that the insulated panel, the inside face will be warm.
Is an insulated metal panel considered continuous insulation?
Yeah, we kind of talked about that earlier. It's not that the definition of continuous insulation excludes metal panels, specifically those with panel joints. But I like to call it consistent insulation because it's outside the structure and you still get a really good U value.
How can the single component insulated metal panel be seen as more reliable than the multi-component rain screen wall system? Isn't one point of failure a concern?
That's a question I hear quite a bit, of course. And so the first thing that I say is looking at that multi-component system, where there's multiple points of failure. And one of the problems there is if there's a failure, let's say in the vapor barrier, how do you know? Because it's concealed, it's inside all this other system. And my examples early in the presentation showing, the moisture inundation in a wall, those sorts of things can happen. But the other thing about an insulated panel is there with that pressure equalized joint with the outside face, the inside face, the sealants, there is some redundancy built into the system of an insulated panel. Obviously, if you punch a hole in it, it's going to fail, but the same thing would apply to a multi-component system. So the failure you're worried about is over time some sort of deterioration, and the insulated panels have proven themselves. That's why we can provide a weather tightness warranty with an insulated panel, because there's practically millions of square feet of them installed, and they're working just fine every day.
What happens if there is a gap in the sealants used with insulated metal panels?
Yes. Well, that's certainly a concern, and that's where that pressure equalization concept comes into play. Because if you have a gap, what you're worried about is, of course, you're going to have some air leakage through that panel. What you don't want is air and moisture leakage through the panel. So that pressure equalization, that's that rain screen principle. It's a properly designed insulated panel with a pressure equalized joint will deal with that pressure differential. It'll equalize it without causing further harm. So it's a redundancy that's built into the panel joinery.
Can an IMP system be used with a bulletproof panel? Does the
Oh,
system work the same, or are there other considerations regarding humidity?
I'd have to defer to some engineers for that question as far as what the bulletproof panel would be and how it would be used. Um, I mean, I would say, I mean, on the surface, can an insulated panel be used with other materials? Yes, as long as there's an understanding of how they will work together. But again, that's really a question for from engineering standpoint. So definitely get with the manufacturer and they can get the engineer involved to help answer such a question.
Great.
Love these questions.
We have 6 more minutes for more questions. Do folks want to add some things in the Q&A? Going once, going twice. Question from Joseph. How do you attach additional material on the outside of the panel without penetrating the panel with supports?
Well, you don't. If you're going to attach something to the outside face, like in the picture you see here, there's a sunscreen shown there. That sunscreen is going to have to attach back to some sort of structure. The consideration there though is to minimize that penetration. You want to penetrate the outside surface and minimize what's going through that panel to the back side of that surface. But you will have a little bit of thermal bridging if you're going to have to do something like this.
Mm. A question from Matthew. What are some negatives of the IMP system?
Negatives. Um, I don't think about I don't think about the negatives, but um, one thing I would say is that an insulated panel isn't for every building wall, every application. You know, if you have a building that has a lot of openings, then maybe an insulated panel isn't, quite the right application. A really cut up building, with a lot of facets and joints and that sort of thing. Maybe there's some situations where it'd be better off to use just other types of materials. But yeah, I'm certainly one that whenever I talk with folks, I say insulated panels are great whenever they're the right application, and there are certainly situations where it's not the right application.
Can you talk about anodized aluminum IMPs? Are they similar?
Well, the anodized aluminum would be the outside face of a system. It, it would be similar to any other, it's an insulated metal panel. So um, your typical insulated metal panel is steel with a painted finish, but I'm certain that I know that there's the ability to use that outside surface. I know stainless steel is used. Certainly, aluminum can be used, um, and it would just be another finish.
Can you talk about how you calculate the carbon footprint of IMPs? What is the carbon footprint of an IMP?
The carbon footprint. So there's of course um, uh, the environmental. Uh, um, oh, I'm kind of drawing a blank of the concept, but yeah, there's of course the metal itself. There's a certain amount of recyclability there, or recycled content. The insulation, the foam itself, typically has a very low recycled content. The chemicals that have been used in polyisocyanurate have improved quite a bit over the years. I used to use halogen type gas for flammability. That's no longer acceptable. Um, so again, it really depends on the manufacturer. And most manufacturers, of course, because we're talking about an efficient system, we're talking about something that has an environmental impact. Um, there is data available on their websites specific to the panel itself.
Great, Tim. Well, that brings us to close. Are there any extra words you'd like to add before I close things up?
I'm thankful for everybody who attended. Appreciate your questions. Those were some great questions. And just hope that you gained something out of the presentation today.
Thanks. I'm going to close it up. Thank
Okay.
you all so much for attending the live webinar, Building the Perfect Wall with Insulated Metal Panels, a CE Strong webinar series powered by the Architects newspaper. This presentation was sponsored by MCA. This webinar is recorded and can be easily replayed using the same registration link. Please allow 7 business days to process certificates of participation and AIA credit reporting for this presentation. A big thank you again to our presenter Tim and to MCA for sponsoring this webinar. We hope to see you all again at a future event. Have a great day.
All right. Thank you, guys. Let's see.